Okay, so um, before continuing with the lesson uh, from last time, um, I would like to mention that I have published the homework description. Uh, was deadline is basically in 2 weeks, and we can go through it quickly together just to check whether there are any questions, and then we'll move on. So uh, this is the description. As you know, the homework gives you the possibility to access uh, 2 to 3 extra bonus points. Um, and this is completely optional. You don't have to do that, so it's not mandatory. And as I have written in the description on Classroom, remember that you cannot exceed 34 points, because last year there were situations where people wanted that. This is not possible, so it's clear to everybody now. Um, so the task is to, first of all, choose among among these environments, one that you like. Basically, they are all games that I have selected. So there is Breakout, Mrs. Pac-Man, Space Invaders. If you click on this link, let's do it together, you'll find them. If you go, okay, so this is OpenAI Gym. There is um, OpenAI Gym basically is a framework that has been developed by OpenAI, which is a company that I've also shown you in the first class when with some videos. And here there are some, most of the Atari games that have been implemented in order to become benchmarks for reinforcement learning algorithms. And so you can look at those environments that I have written in here. You select one of that, and your assignment will be to basically implement that environment. You can take that as a reference, so the real implementation. What you'll have to do is basically implementing the dynamics of that environment. I don't want any, I mean, actually, I don't ask for, if you want to do it, it's not, you can, but it's not required. There is no obligation for you to create any kind of rendering or visualization, except even a print is enough. You don't have to do anything fancy. If you want, you're welcome. Otherwise, it's okay. So what does it mean to implement that environment in Python, of course? It means to basically create an environment according to the interface that is specified in the documentation of OpenAI Gym. The interface, if you don't know what an interface is, here there is an answer on Stack Overflow regarding that. But in general, it's basically the contract that defines the methods of your classes. So with inputs and outputs that are quite clear. Um, so you have to create an environment using that interface in a similar way to what I did in my Python notebooks right here. I create my environment similar way, very similar way, right? This is an environment where the render function is just a print, so you can do exactly something similar to that. And you will have to use only discrete states. You don't have to create images, as I mentioned. You can return the real state of the environment, also because the environment has to be fully observable. You have to use the reduced state space. Here you have, in these games, you have quite big state spaces. Right? In this Pac-Man here, you have, I don't know how many columns and rows, but for us, for our purpose, is enough or even too much a 10 by 10, 10 by 10 grid. So of course, not 2 by 2, but 5 by 5 is acceptable. And for example, if you're implementing Mrs. Pacman, again, there are some simplifications here. You don't have to implement the ghosts that move. So you have to use static ghosts, and in that case, I mean, if you use a grid of 10 by 10, you should adapt the number of ghosts according to the size uh, of your environment. Similarly, for space invaders, the invaders are static. You don't have to have them moving. So basically, except the agent, everything is static. You only have discrete actions, and to get 2 points, it's enough to create an environment and write a simple test program where basically you create an instance of your environment and you choose 5 random actions, you execute them, and this is enough. And you show the observation that you get. If you want to get 1 more point, then you expose the transition model. This means you use the transition model that is internal to your environment and you implement the policy iteration algorithm. And let me stress this, no groups are allowed. Each homework is for one person, one single person, and plagiarism is not accepted in any form. I will be verifying that between students, previous students, and internet archives. So everything. And in case of plagiarism, not only you will not receive the bonus points, but I will also detract 3 points from your final score. So it's strongly, and you shouldn't do that. And now, if you have questions regarding this, post them on Slido now, and then otherwise we'll move on. Do you have questions? Is this homework one of the 3 total? No. You should consider this part of the course as a separate section, independent of the other one. Okay, so machine learning, it's like, it's composed of 2 courses. One is a 6-credit course, machine learning, and the other one is a 3-credit course, which is reinforcement learning, which is this part, which has its own rules and its own mechanism. Except the only difference, the only conjunction between these 2 parts is the fact that you, in the end, your final score will be a weighted average of the 2 parts. And of course, there are notions that are related one to the other, but nothing more than that. Do we have to implement one of the environments in OpenAI or create one from scratch? I mean, it's the same thing in the sense that you have to look at one of these environments. So for example, let's look Mrs. Pacman, for example, or Breakout, which is here. Right? So you should look at how this environment works. You can also look at the code, view source on GitHub. You can see how that is implemented more or less. But then you take the overall ideas that are here and you see how an environment is implemented in OpenAI. And then you go back, you open your editor, your IDE, and you start implementing it from scratch. It's more simple than what you expect. I mean, don't be scared by this thing, because it's at most 1 day of work, at most. But I mean, 1 day, I mean a couple of hours, not more than that. What is considered plagiarism? If you copy, paste code, or I mean, you just change the name of the variables, that's plagiarism. Yeah. You should be, I mean, understanding what's happening. If by any chance I understand that this is not the case, you're not going to get the score. Any other question? Okay, so and I'll get back to Slido later. If you have more questions, post them, but we'll move on. So what did we do last time? We talked about temporal difference learning. And we said that temporal difference learning is sort of an intermediate between Monte Carlo methods that we have seen previously and dynamic programming. It's similar to Monte Carlo methods in the sense that it only uses experiences and it doesn't know the transition model. But similarly to um, dynamic programming, basically temporal difference methods um, um, exploit the Bellman equation and estimate the value function um, of a certain policy by relying on previous estimates. And this process is called bootstrapping. Hmm? So we have seen a very simple temporal difference method for policy evaluation. Remember that we have two parts that are similar to the policy iteration algorithm that we typically use in reinforcement learning, um, while policy iteration is a planning method, so we cannot use that exactly, but we can do something similar. And um, this process is basically composed by two steps. One is we start with a policy, we evaluate the quality of that policy, and then we take an improvement step. And then we reevaluate and we take another improvement step, and so on and so forth. Okay? We also said that the overall equation for updating the estimate of the value function doesn't really change in the sense that the overall structure it is always the same, which is previous estimate gets previous estimate plus step size alpha that multiplies the difference between the target and the current estimate, where this difference between the current and then the current estimate and the target is called, it's the error, and we are taking a step in the direction of decreasing the error. Now, the difference between temporal difference methods and Monte Carlo methods is only in the target. So this target is different for Monte Carlo and for temporal difference methods. How is it different? In Monte Carlo methods, here you have the full return, right? Where you basically sum all the rewards and you discount them until the end of your episode, while in temporal difference methods, you don't need to wait the end of your episode, so you don't need to estimate the full return, because you do that in approximation by taking a single reward and summing to it the current estimate of the value of the next state. Remember that this is in expectation exactly the return. So semantically, there is not a big difference. And in fact, we have shown that they are equivalent. Monte Carlo methods and temporal difference methods are equivalent in when the value function is not updated until the end of your episode, which is, however, not currently not. I mean, what not happens doesn't happen in these methods, because you take a single transition and you update your value function. Okay. Um, So we have seen these concepts. We have seen also the difference between sample updates and expected updates, where in the dynamic programmings, we use expected updates for our value function, while because we use the complete distribution of all possible successors by using the transition function that is known because we are doing planning, while in temporal difference methods and Monte Carlo methods, we rely only on experience, so we don't have the transition model, and we use sample updates, meaning that we sample transitions, we sample trajectories of state action rewards, and we use this to estimate our value function. Yeah, we have defined the TD error, which is nothing else than the error that I was talking about before, where the target is the temporal difference target, which is this one, right? Reward that you get plus the estimate discounted of the value of the next state. we have seen also in practice, what does it mean? I mean, what is the actual difference between these two methods in updating the value function, how these two behave in a different way? We have discussed quickly the advantages of both methods. We have seen some examples, and I think, yeah, okay. So we have also seen to actual implementation of these algorithms, in the sense that beyond the policy evaluation step done with TD0, we said, okay, what if we want to implement the full reinforcement learning algorithm, where we have both the policy improvement and the policy evaluation step? So in order to do that, similarly to what we have done for Monte Carlo methods, we have introduced both on-policy and off-policy methods. Remember that in on-policy methods, you are learning about the same policy that generates your data, while in off-policy methods, you have two policies, one of which is the target policy, which is the one that you are trying to learn, and the other one is the behavior policy, which is the policy that um, generates your data, the one that is being executed. We have also seen some examples about this last time, so I will not go through them again. Um, okay, so we have seen that in this case, a non-policy algorithm is a very famous one, is SARSA, where we are using the Q function, of course, instead of the value function, the actions value function, because we want to do control, so we need to know what action is better to take without knowing the transition function. And given that we need to evaluate the quality of a state and an action, we need to know which action, right? We need to do that for in the next state. And this determines the difference between a non-policy and off-policy algorithm here. For example, in SARSA, the action selection for the next state is done by using the same policy. So this action is sampled from the policy that we are learning about. Okay, so this converges with probability one to the optimal policy and the optimal Q function, as long as all the states in action are visited. But we have also seen in some example that this also takes the action selection over time. With SARSA, we are estimating in the policy evaluation step, we are estimating the value of the policy. So again, exactly the policy, if we want to generalize the discussion about the target policy and the behavior policy, the target policy and the behavior policy coincide, they are the same, it's a single one. In QLearning, we are estimating, we are evaluating the optimal policy, which is why we are taking a maximum step here. So this is our target policy, while the behavior policy will be an epsilon greedy policy that is based on the Q function. But here we are estimating the value of the optimal policy, and the optimal policy is the policy that maximizes the Q function at every time. So here we are not estimating the value of the behavior policy, but we are estimating directly the value of the optimal policy. So we have seen one example related to this, where in the blue path, which is the one generated by SARSA, we basically take the action selection into account, because the policy is epsilon greedy, and also the environment is sometimes can let you fall in the cliff if you move too close to this. And then in this case, SARSA prefers a safer path, while the optimal path, that is the one that QLearning, that is the closer to the cliff, is the one that QLearning learns directly. And I think we stopped here, basically. This was the last thing that we have seen last time. So we have seen that SARSA in practice learns a longer and safer path that also results, however, in a better reward in this time in this specific task because there is no occasion where this falls in the cliff. When I started this summary regarding temporal difference methods, I said that temporal difference methods rely on uh, I mean, the Bellman equation, and they are similar to dynamic programming. So now, here we have the Bellman equation, where this is what we have seen for planning. So we have said that the value of a certain state is equal to the reward plus the discount of the maximum of the values of all the possible successors, right? Okay. Now, first of all, if we know what is the notion, the relation between the value function and the Q function, we can do something regarding that. So what is this relation? The relation is that the value of a certain state is just the value of the maximum action. So you take the Q function and you do the max over the actions, and that gives you the value of a certain state. So if we write down this Bellman equation now in the form of the Q function, right? So it's nothing else than replacing, plugging in here this relation, right? So we said that this is the sum of the reward plus gamma that multiplies this thing over here, where we can get rid of the uh, maximum here because this is already doing it internally, right? You see that? Do you understand this step? At least in class, I can see the feedback. The max, why this max disappears? Well, because this is not anymore the value. So the maximum here is because it's V. So if now this is Q, you can get rid of the max. Huh? So given that this is Q, we get rid of this max, and then we write the equation without the maximum. And now we replace this V over here with this extended definition, internal. So V equals to the maximum of A. Now in S prime, which is the next step, here there is a typo. Here there should be prime. So basically, this is very similar to what we see from the QLearning update, except that we don't use the transition function. And in fact, in expectation, that's exactly the same thing. So if you look at the QLearning formula, this is reward plus gamma max QSTA. Now this is done in an iterative way. That's why you have these two additional steps over here. But this is the Bellman equation, really, without the transition function known. So if you have questions on this post-demo slide, we can get back to it anytime during this class. Now, there is also another alternative to sample updates, which is something similar to what we do in dynamic programming, except that we take the expectation, we compute the full expectation using the policy. This is the case of expected SARSA. So basically, this is the same, very similar to SARSA or QLearning, except that instead of the max, in the case of QLearning, we use the expected value. So we replace the maximum with the expectation, right, over the policy for a certain action to be taken. So this is an intermediate layer really between what SARSA does and QLearning does, because QLearning takes the maximum operator, SARSA takes the action selection of the policy. Here we are taking all the possible actions weighted by their probability of being selected by the policy. So basically this expected SARSA algorithm will move in a deterministic way in the same direction as SARSA moves in expectation, because here we are computing the full expectation. It's of course more complex than SARSA, but there is also less variance. And uh, yeah, you can see that there is this difference. So, I mean, here there is some plot where we are looking at the sum of the rewards for each episode while we change the step size. And we see that if we increase too much the step size, with SARSA, the performance asymptotically decreases, right? In QLearning, this is less of a problem, also because we are computing directly the optimal policy, and expected SARSA instead behaves in a more stable way. Okay, so now if you were in class, I would ask, is expected SARSA, in your opinion, an off-policy or an on-policy algorithm? Now the answer is it's an off-policy algorithm. Why? Because it uses a different a behavior policy that is different from the target one, right? So if pi, which is the target, is greedy, um, then we are doing, that is the behavior policy, while the target one is using the full distribution. So it's not the same thing. Also, one thing to notice is that if the target policy is greedy and the behavior policy is exploratory, then expected SARSA is the same as QLearning. Why? Just because if you plug in a target policy that is greedy, that is just doing the max, right? So it means that selects only one single action. And the behavior policy is exploratory, then you're doing the same thing as you do in QLearning. So we have also noticed from this plot that we can have a step size in expected SARSA that it can be huge, equal to 1, which is big, without degrading the performance. Now, let's take another step. So we have seen 3 temporal difference algorithms: SARSA, QLearning, and expected SARSA. They have all they have their own peculiarities. But let's reason a bit more on QLearning. So in QLearning, we do max, right? We have said QLearning, we take the maximum over the Q function of the next state, right? For estimating the next value. This is a problem, right? We have discussed this also when we introduced the bandit problems. If you take the maximum, right, then you are introducing a bias, because if this is an estimation error, then you are always overestimating some action. So for example, consider a state where many actions have a value that is a Q value which is 0, but you have this uncertainty in your estimate, so some are above and some below threshold, below 0, and this is because you're doing estimation, so there is some uncertainty over there. Then you take the maximum, and if the true value is 0, you're taking the maximum or estimates that are leading you towards the positive side of this error in your estimation, and this means that you are overestimating your Q function for a certain state and action. This is a problem, and this is why we typically introduce double learning, which is a trick that if you look at the DeepQN paper, which is the one that has been used to solve the Atari games with superhuman performance, We have seen that in the videos, the first class. Then they use also double learning. So double learning is very simple and basically relies on this idea that by taking the maximum operator, you are overestimating your value function. And given that that is the problem, what we can do is independently learn two different estimates, where one is used to maximize the action. So you take the maximum over that value function, and the other one is the real estimate of your value. So you're estimating or updating just one of these two on each episode and using the other one for um, uh, taking the maximum. So this is called double learning. Um, and basically it behaves as follows. It's nothing else than really QLearning, except that you have these two value functions, and with 0.5 probability, you either update one or the other, and you take the argmax over over sorry, you take the maximum over the other one. So you use your estimate by taking the action as maximizing the one the Q1 in this case. So if you are updating Q1, you take the argmax over Q1, but you use for your estimate Q2. Right? You update your Q function using Q2 by taking the action over Q1 and vice versa. So you are decorrelating your data so that if you take an action by maximizing by maximizing Q1, then in that case you are using the value coming from Q2 so that they are not related. Hmm? So, and if you look at one example here, without going too much into the details of it, you will see that while QLearning has this overshooting here, where it initially overestimates everything, and then it has to correct that, double QLearning doesn't have that. So now this set of slides is complete. We have time for some questions, and then I'll go to the Python notebook for temporal difference learning, and then we'll move on with the next topic. I mean, while you ask questions related to the slides, if you have, so for the homework, there is no report. You have to deliver your code. And let me add, it has to be well documented. You have to document your code, please. Explain, I don't want to say line by line, but almost what you're doing in your code. So I will say this here, I will add this also in Classroom. If your code is not well documented, I'll send it back to you, asking you to document that, okay? But anyway, there is not a report beyond that. And the final exam will be a project, yes. It will be a project. Other questions? You have question in class here? No? Okay. So let's wait a couple of minutes for questions, and then we'll switch to the Python notebook. Okay, so it seems there are no incoming questions. Maybe some will come while looking at the code. So the code is the following. So I'm not going again through the MDP because it's the same as the last two times. So it's a grid word where you have pits, a goal, you have walls where you cannot walk in, and you have four actions that are up, left, down, and right, and an agent that has to reach the goal without falling in a pit. So the agent is your X, is this X here, and this is the grid, and it has to move from the initial location to the goal, avoiding the pits. And actually, the structure of it is slightly changed with respect. So the code is the same. The structure of this grid word is slightly different and reflects what we have seen in the slide. So it's this one, it's this environment here. So these are all bits where you get -100 reward. Um, and then the agent starts here and it has to go in the final goal location. So the code, again, is the same, except the instantiation of it is slightly different. And similar to what I have done for the Monte Carlo methods, I created in both for QLearning and SARSA here uh, some functions that will compute my policy by starting from a Q function that is a table here. Specifically, it's a dictionary. So where this dictionary is mapping an integer to a list of floats, where this list corresponds to the values of all the actions, right? So the int here is the state, where I'm pre-processing the state to be mapped to a specific integer, okay? And then the policy, right, in QLearning is computed by simply taking the argmax of Q with probability greater than epsilon, otherwise is a random action. It's an epsilon greedy policy. Okay. So nothing new in the preprocess state and in the way to compute the Q function, except that last time we had a table where we also stored all the returns, and by using the returns, we estimated the Q function every time. Here we are using directly the Q function because we don't need the return, so we can take step by step the update of the value function. So I mean, this is basically a complete reinforcement learning algorithm. For every episode, we reset the environment, we take our policy, and until the environment terminates, there is a final a terminal transition or maximum length episode. So until we reach that number of steps, we take the state from the environment, we pre-process that, we pass it to the policy will give us an action, right? And again, if we want to look at the internal of this, the policy is computed, takes the state, looks at the state, and it just looks internally at the value function and it does the argmax. So nothing weird, except that there is the epsilon greedy part, but it's nothing strange there. So then, by taking the action, I pass it to the step function of my environment, which returns a transition that will contain information about what was the previous state, the action that was taken, the reward, the termination, and the next state. I take the next state and I compute my target as the reward coming from the transition plus 1 minus termination, right? Because this is what we said the last time. If the state is terminal, I don't need to sum the value of the next state anymore because there is no next state. So if this is terminal, I will not sum anything. So this trick allows you to get this part to 0. But otherwise, if this is not terminal, I some gamma that multiplies the maximum of the Q of the next state. And that's it. So this becomes my target. And then I compute my Q function update as usual, because this is the generic formula, as Q new estimate becomes previous estimate plus alpha multiplying target minus previous estimate. So again, if I want to do a different algorithm, I just replace the target, and you will see that this is what I will do with SARSA. I will just change this and nothing else. Huh? Okay, then if the transition says that this is a terminal state, I will break out of this loop and continue to the next episode. So I run a bunch of episodes, specifically it's basically 2,000 episodes, and you will see that my agent will start moving right, and then it will go up, right, 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 right. So it's moving towards the goal, right, right, right. Now, here it went up. Why? Because in my in this code here, I didn't remove the stochasticity of the environment. So this can lead to some weird transitions that were unexpected. So moving, the agent was anyway moving, sorry, here was moving right. Sorry, I said that there is stochasticity in the environment, which is true. But in this case, this specific move to up it's not due to the learning itself. It's due to something that I did. Is my um, problem, let's say, is that, which is the fact that I didn't remove the epsilon in the policy, right? Because I didn't set the evaluation mode. Typically, when you evaluate your policy, when you are executing your policy after learning, you want to set your epsilon to 0. So that this doesn't happen. Instead I left it to 0.01 or whatever was the value that I selected. So that's why this was going up. But if you remove that and you leave it to 0, as it should be, then this will move right normally. But I mean, there is some stochasticity also in the policy here, which shouldn't be, because it should be, just the argmax of the Q function. Not during learning, but at evaluation time, meaning when you are executing your policy to see how good it is. Okay, anyway, it's completing by moving right, right, right. And it goes until it reaches the end of the grid, and then it goes down. Similar to what we have seen in these slides. Right? This is exactly what we were expecting to learn from QLearning. Right? A path that was very, very close to the cliff. Now, I hope this is helpful, because you are seeing in practice what is coming from the theory, right? So this was the expected outcome, and this is what you see in practice. Now, in SARSA, I'm not changing anything in the code, except that here, sorry, it's very hard to move with this trackpad over here. So SARSA, okay, here. Not changing anything, except that I'm computing an X action, right? So, sorry, and next state and a next action. And then I'm using that in order to compute my target, and using this next action, and that's really it. The target is the same. It doesn't really change anything else. So now I run the learning for the same amount of time, and you will see that the policy now will behave differently, which is it will go up, right, 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 until it reaches the end of this thing over here of the grid, and then it moves down. which is what we were expecting from SARSA. So as you have seen, I basically, in these algorithms, I've just changed the target, nothing else. That's how these algorithms are created. Now, not all algorithms are this simple, in the sense that, especially when you will be looking at algorithms that are implemented for solving state-of-the-art benchmarks, like the ones that we have seen in the videos in the previous class, then things are slightly different and they use neural networks instead of tables, but the idea is the same. Um, Let me also say, and I'll discuss how you can do now this with a neural network, because we did it also last time. But let me say that, at least for QLearning, there is not a lot of difference with the deep QLearning algorithm that was the one that solved the Atari games. So there is some difference, but not a lot. So I will discuss now what these differences are, just for your for helping you in understanding this, and also because QLearning is anyway one of the algorithms. Sorry, deep QLearning will be one of the algorithms that you will be working on the projects. Okay, so what's the difference between standard QLearning and deep QLearning? First of all, we're using a neural network. So what does it mean that we're using a neural network? It means that this step here is not exactly like this. It's similar, but it's not exactly like this. So we still compute our target in a very similar way to this. Exactly, I mean, the target is computed in the same way. But now, first of all, we don't want the gradients to go through this part of the estimation, because this has to be fixed. So we basically block the gradients for the target, and that's one thing. And the other thing is that this becomes an L2 loss, where we are doing, L2 loss is a mean square error, nothing else than that, where we are taking our neural network, we're taking it, and we are basically computing the difference between this target and the output of the neural network, and then squaring that and uh, trying to optimize by taking a gradient descent step in the direction that minimizes that this error. Now, this internally to the neural network, something similar to this is happening, not exactly the same, but something similar is happening. Internally, you're taking a direction a step in the direction that decreases the uh, error, and then this is doable using gradient descent because the neural network is a differentiable function. Here we have a table, and it's just a table, so we do the manual update. But you don't have to worry about that, because you have your optimizer like Adam or SD, stochastic gradient descent, or whatever you're using, that will do that for you. So you just create your loss and you say optimizer.optimize. The other difference with the deep QLearning algorithm is that instead of taking transitions as they come, so when you take a transition, you store that in a buffer somewhere in a memory, and you do your updates, you compute your targets, and you do your updates by sampling from this memory your data. This is just for decorrelating your data, because when you use neural networks, you want your data to be independent and identically distributed, which is not the case here, because you're collecting transitions that are related one to the other, because you have states that determine the next states. So in order to reduce this problem, you store your data in your memory and you sample from it, so that your data are basically all shuffled, and you don't do that in a non-IID setting. So this helps the neural network itself. And the other thing is that you do something similar to the double QLearning that we have seen, except that it's not exactly the double QLearning. So you compute your target by using, you have two neural networks. You use your target by using the target neural network, and you update your learning neural network, and every once in a while you update your target neural network by copying the weights of your learning network. So you just basically say, now these two networks are the same. Huh? They're still different, they are still separate, but they will have the same weights, so they will emit the same outputs. And then I will do again what I did before. So I will update only the learning network and keep this fixed so that at least there is not a moving target. Right? Because if you keep updating something based on the same thing, this is moving, 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 and it's hard to follow. While if you keep this fixed for a while, at least you're able to reach your target, and then by updating your target neural network, you can move on to further improve your estimates. And this is basically DQN. There is nothing more than these couple of tricks that I mentioned, and the fact that you're using a neural network. Of course, the neural network will be, for example, for dealing with Atari games that give you as the state in the form of an image, then it will be a convolutional neural network. But the idea is not different. You can do the same even if you don't have images with a normal feed-forward neural network, and you're done. Okay, so, and similarly for SARSA, nothing, nothing else. Okay, questions? Or curiosities, if you don't have questions. You mean more or less means something. Okay. Again, I hope looking at implementation can help you. Yeah, that's really what you need to focus on. In order to learn reinforcement learning, you need, similar to what you do in reinforcement learning, you need to do trial and error. So implement things and try them out, see, and then try to understand why something doesn't work or it works. And yeah, so it's mostly implementing things, I would say. Anyway, no questions are coming, so we'll move on to n-step bootstrapping and model-based reinforcement learning. So n-step TD methods basically unify Monte Carlo and one-step TD methods because they are doing something intermediate between those. So in Monte Carlo methods, we wait until the full return. In temporal difference methods, we don't compute the return, but we use a single transition. In n-step TD methods, we'll use the TD update rule, but still using some return that is computed over, for example, the next, over 10 time steps, for example, instead of the full return. Why do we want to do this? Because one step might not be enough to get significant state changes, especially in very sparse settings, where sparse settings means that your reward comes maybe only in a single state. So there is a lot of sparsity in this signal. And so the solution is we still do bootstrapping, but we do it over multiple steps. Okay, so as usual, we divide our problem in a prediction and control, or policy evaluation and policy improvement. So we want to estimate the value of a certain policy, and we do that from sampling transitions on the episodes that are generated by using the policy that we are trying to estimate the value for. So in the Monte Carlo update, as usual, as we said, I don't know, I think 100 times already, we use the full episode, we wait until the end of the episode, we compute the return as the sum of the rewards discounted, and we use that as our target, for our targets. In one-step TD, like SARSA, QLearning, expected SARSA TD0 that we have seen, we do our updates based on the next reward and the value of the next state. The intermediate approach is update based on a certain number of rewards. So you wait until you receive 10 rewards, and then you sum these, and at the end you sum the value of the estimated value of the 10th state. Huh? So this is still temporal difference because you are still doing bootstrapping, but now you're looking 10 steps ahead. And this is exactly what I mean, this is a schema that is showing you exactly the same. So this is one step TD, TD0, SARSA, QLearning, whatever. This is two-step TD, so we're waiting 2 steps. And then we do, here you have a bootstrapping step. Three-step TD, you wait 3 transitions, and here you have a bootstrapping step. And step TD, you will wait n transitions, and at the end of this n, you will have a bootstrapping step. Infinite TD or Monte Carlo is, you don't have any bootstrapping, you wait until termination, you sum the rewards. This is unifying the notion of all these algorithms, right? So the overall idea doesn't change, but it's just unifying all of this. So as usual, we want to compute our target. So, and we do this, again, in relation to what we have seen. So Monte Carlo, one-step TD, and so on and so forth. Monte Carlo, we estimate the full return as the sum of all the rewards discounted. One-step TD, we do sum of the reward plus the estimated value of the next state discounted. Now in the two-step TD, we compute the two-step return, which is the current reward, the next reward discounted, plus the value estimated of the next, state coming after 2 steps. Similar step return will be the same thing, except done after the n steps. So this is approximating the full return, except that is truncated after n steps. So this means in practice that you need to wait until you see a certain number of rewards, and then you can do your update. So this is the pseudocode of the algorithm that is just explaining you the same thing that I just described in words. So, I mean, I think the idea is clear. We don't need to go through it in detail because it's exactly what I have described, just in a formal way. Now, you have some properties of these algorithms that are, of course, the fact that in expectation, the expectation of the n-step returns is guaranteed to be a better state, sorry, a better estimate of the value, right? Similarly to what we have seen for the temporal difference error, one-step temporal difference error, this is guaranteed to be a better estimate. Now, we have said that temporal difference methods are very good because you don't need to wait a lot of time. You can, they're better for credit assignment and some other properties that are also the fact that there is less variance compared to Monte Carlo methods. The fact that you're using an n-step returns means also that you have some you are trying to get the best of both worlds. Monte Carlo methods are good because they are also more accurate in some sense because they are based on actual data instead of relying on estimates, which means that they are more stable in in the long term, while still there is more variance because you are collecting full trajectories. This is, I mean, taking the best of both worlds. Um, so you are reducing the variance compared to Monte Carlo algorithms and compared to temporal difference method 1 TD methods. Then you are uh, being more accurate in your estimates. So for these algorithms, there are formal proof that this is converging to the correct prediction. Um, Now, 1 TD and Monte Carlo are just extreme numbers of this, and there is, I mean, basically in some tasks, you can see that having a n which is too big or too small can potentially bring to worse performances. So here we are seeing a plot of the root mean square error of the values estimated over 19 states after 10 episodes by changing alpha. You can see that if you take the value of n being 1, which is the case of TD, normal TD like SARSA or TD0 or whatever, then the root mean square error is higher in its lower point when alpha is 0.8 in this case, compared to n being 4, for example, where n is the number of steps that you're looking at, so the number of transitions that you're waiting to estimate your, to update your estimate of the value function. You can also see that this converges to better estimate with a lower alpha. So all these algorithms are sensitive to this parameter. If you set the same alpha for n equal 4 and n equal 1, so at 0.8, for example, this n equal 1 will be at its best value, while n equal 4 will be at almost at its worst value. So there is some tuning that needs to be done, like all machine learning algorithms. Some hyperparameter tuning. Practice, this can require some time, but this is how life goes. Now, let's plug this in, some complete reinforcement learning algorithm. Again, meaning that we have not only the policy evaluation part, but also the policy improvement step. And this can be done by considering, for example, a non-policy algorithm, which is n-step SARSA, which is nothing else than SARSA, the same thing that SARSA does, except that we do it at the final step where we are taking the estimation. So our target would be computed as the sum of the rewards until the end state. And in the end state, we take the Q coming from that state and the action that the policy would select in that state. So the algorithm update in the end will be the same, the usual one, where the target is computed in this way. Now, the same diagram that we have seen before can be extended to SARSA specifically. So we have one-step SARSA, we have two-step SARSA, three-step SARSA, and step SARSA, so on and so forth. Now, this black dot here represents the action selection, and this represents the state. So here we're taking an action, we're getting a next state, and we're taking also the next action. So this is what is being considered. And here in two-step SARSA, we start with an action, we take a state, we take another action, we take a next state, and from here, we compute the value of Q in the state and the action that is being selected here. So this is the second step. Three-step SARSA, similar thing, and step SARSA. Infinite step SARSA is again Monte Carlo methods. And there is also n-step expected SARSA where in the nth step, instead of doing the action selection considering the policy, you do the full expectation based on the policy, meaning, again, that you consider all the actions and you weight them by the probability that the policy would assign to that action. So we are considering all of these in the discrete case, which is why you can enumerate all the actions. If you are dealing with a continuous action space, then there is some complication in all of this, especially for the step for the expected SARSA. How would you do that? You would sample a bunch of actions from the action space and then compute the expectation based on that. So there is another degree of uncertainty added. And this is the pseudocode of n-step SARSA, where, I mean, this is again what we have just seen. I'm not going to read the pseudocode. So what are the benefits in practice of all of this? So if you have an environment with sparse rewards, right, like in this case, where the reward is zero, so you have no signal at all except in the goal. And then let's say this is the path that your agent has taken. If you consider one-step SARSA, this is only, I mean, after one update, one single update, using this trajectory, so transitions coming from here, this will be the only state that will have some value different than zero, right? Because you take your updates to all this state. This is looking at the value of this state, which is zero. Looking at the value of this state, this is zero. This is 0, 0, 0, 0, 0, 0, 0 everywhere. Now we reach the terminal state, and this is telling you, okay, this is a terminal state, but I have a reward. So this is the value that I will assign to this state. If you do 10-step SARSA, this is slightly different though, because you are back propagating this. I'm using back propagation as a term, which is not the same as neural network back propagation, of course, but you are backtracking, let's say, backtracking this information from G 10 states back, 10 states back. So your this information here will still have the bootstrap being zero because this is a terminal state, but in this state our value will be the reward that you get in the goal discounted 10 times. So would be gamma elevated by 10 that multiplies the reward that you get in the goal. Again, we have seen expected SARSA and step expected SARSA is the same as we just discussed. We just take the expectation step. Now, can we do off-policy learning using n-step transitions? N-step, considering n-step algorithms? The answer is yes. As usual, you have the behavior and the target policy. You compute your returns over the n steps, and you want to compute the relative probability of the actions, of these n actions that have been selected by the agents, as they were selected by the behavior policy, and how likely they would be selected by the target policy. So we are computing again, these weights, these important sampling ratios, in the same way as we did for Monte Carlo methods, except that we are truncating this at the horizon after n steps. So it's the same notion. There is nothing else than what we already discussed for important sampling ratios, except that these are being truncated where the small trajectory that you have terminates. Okay, so I mean, if we want to go again back to this, what is the behavior of these important sampling weights? It's just that if let's say some trajectory has been sampled by the behavior policy, if pi, the target policy, would never choose this action, then the n step returns gets zero weight or a very small weight if this is different than zero. Never is an extreme. If pi would take this with probability much larger than b, then the weight is increased, and so that data that are rare become overweighted so that they count more. If the policies are the same, this ratio is 1, so you see that it goes back to the SARSA setting. Now, we have seen QLearning, and in QLearning we didn't have any important sampling ratios, and similarly in expected SARSA, and they were still off-policy algorithms. So we can do off-policy learning without important sampling ratios. How? So the general approach is that you have this tree backup return that is computed, where non-selected actions contribute by a certain weight that depends on their probability, while the selected actions weight the second level actions, right? So if you don't select an action, you weight, you use the weight that comes from your probability of selecting that action. If you select that action, then this weight is still computed, but is multiplying everything that is coming after. So you are expanding your tree. So in the one-step case, this is the same as expected SARSA because you don't have to expand your tree anymore. You're stopping here. So this is expected SARSA. You're taking the expectation, so the probability weighting all the actions, so the value of all the possible actions by their probability of being selected, and you don't have to expand anything here. If you have two steps, then we can look at this formula here. You are taking the reward, summing that to the value of all the non-selected actions weighted by their probability, plus the probability of the action that is instead selected, that multiplies the next reward, and so the second reward, and the value of the second state and the action. Here we are taking a full expectation over all the possible actions because we are stopping at 2 steps. If this was 3 steps, we would have had 2 terms also inside here, one where we have all the non-selected actions and another one where you have all the selected actions. So the general definition of this is this one, which is in a recursive definition, but it's exactly what we have just discussed here. So it's recursive definition because we're saying we take the expectation of all the non-selected actions plus the weight of the selected actions that multiplies the return in the expected return of the steps coming after, so from t plus 1. And this is the pseudocode. And again, it's just what we have discussed. Now, in this case, we are doing in this case, we are doing expected updates because we are considering the full expectation related to the probability. In the case of SARSA, we are doing sample updates, even an n-step sample updates. So what are the pros and cons of all of this? So the sample updates consider one single sample, of course. So this means that they are affected by sampling errors, which goes quickly down. However, if the branching factor is large, as in terms of being a con, it's cheap to compute. However, so if you have a large action space, you prefer to be cheap rather than to compute all the possible alternatives. While in the expected updates, of course, this is more exact. So you are computing your weight in a better way because this is an exact estimation of your a possible update without the transition model, of course. Um, but they require more computation, and this is more similar to what you do, in fact, in planning. So if you don't have a distribution model of your policy, however, this is impossible to be done. So if the environment is deterministic, expected and sample updates are identical, we can unify all these algorithms where, so n-step SARSA has all sample transitions, n-step expected SARSA has all so I expected updates. I don't know why I have written sample up transitions here. This is a typo. So there is the full branching. No, sorry, my mistake. And step expected SARS has all sample transitions, exactly, yes, except the last one. While the tree backup algorithm has all the full branching without sampling. Now, we can unify all these algorithms by creating an algorithm that we call Q sigma, where sigma is a factor that controls the degree of sampling. So 1 means full sampling, 0 means pure expectation. So that you have something like this. Here. If you look at this scenario here, you have Q sigma, where sigma is 1. Here you're taking a sample step. Sigma is 0, you're taking an expected step. Sigma 1, you're taking a sample step. Sigma 0, you're taking an expected step. So you can have a mixture of these situations. Okay. So the Q sigma algorithm is described over here, where basically it's not really changing a lot from what we have discussed. You will see a lot of complicated formulas. You don't need to go through them in very details, except that you will see that this sigma is controlling whether you're doing sampling or not. So you have 1 minus sigma that is telling you 1 minus sigma. If sigma is 1, then you're doing sampling, meaning that you are zeroing all this part where you are doing the expectation, and that's it. Now, I would like to pause it here before moving on and see if there are questions. Can you repeat your question? No, you choose it. So you choose sigma. This is you, algorithm designer or engineer, select sigma. See, in the pseudocode it's written select and store sigma. So it's you that controls that, and controlling that. If you look at this pseudocode, in any case, the last, almost the last line here, you see that the general update rule is still always the same. It's just G that is the target that is computed in a different way. Okay. Other questions? You? No. Okay. No questions. I must have been very clear today. So we introduce now very quickly, and maybe we'll continue next time, model-based reinforcement learning. So until now, we have been in a model-free setting, meaning we said we don't know the model, we just do learning by experience, and we use that in order to improve our policy and estimates of the values. Um, so in model-free reinforcement learning, we relied on pure learning, pure experience. We um, have seen that we can use sample updates, expected updates, and so on and so forth. In model-based reinforcement learning, we do planning in addition to learning, but planning on a learned model. So the model, again, at the beginning is unknown. The agent collects experiences from the environment, from the world, and based on these experiences tries to build a model of the world, of the environment, and uses this in order to compute its policy, in addition to maybe doing something similar to what we have seen already. So there is an additional planning step that is done on a learned model. So let me stress this. At the beginning, the model is unknown in both cases. In model-based reinforcement learning, we try to build our model. So, sorry. They are different in their own ways, but there are also some similarities in the fact that both will rely on a value function or on a policy. They will use look ahead to future events, or they use backup values. So what's the goal of these models then? When the agent is exploring the environment, it's trying to build a model for what? It's trying to build a model that will be basically used to simulate experience. So it's like we uh, we act in the world, we see things happening, and in our mind, in our imagination, we can start thinking on what would be the consequences of our actions because we experienced them before. This is a very similar thing. Um, we can build two kinds of different models. One is you can have sample models or distribution models. So in sample models, you will basically produce one single possible transition given a state and an action. So if I say, this is the state that I'm currently in, and this is the action that I want to take, then tell me what would be the next state and what would be the next reward and termination. In distribution models, you generate all the possible transitions weighted by some probability. So you consider all the possible options that can come out. Um, so with a sample model, you can generate a full episode, of course, until termination, given a starting state and a certain policy. In distribution model, you can generate all the possible trajectories, all the possible episodes. So sample models, one single episode. In distribution model, all the possible episodes that can come out from a certain state by following a certain policy. Okay. So we said you can do, by using these models, you can do planning. Now, you have different kinds of planning. One is the dynamic programming one that we have seen, that is planning on the state space, right? So where we compute the values and the actions cause transitions from state to state. So you're searching throughout the state space for an optimal policy or a path to the goal. And there is also plan space planning, which is searching through the possible space of plans. This is similar if you're doing AI currently with Professor Nardi. I don't know if you did already the planning part. Did you do that already? So POP, you have seen that already. That's the plan space planning. Now, this is slightly different from the classical planning definition, because in the classical planning, you use symbols and all of that. We use numbers. This is a more numerical planning, but still planning. So You cannot rely on symbols to do to apply methods like the ones that they use in classical AI, but we still do something similar in the sense that we back up values, right? They do the search from the goal to the start. We do something similar in the sense that we try to expand everything that we have until a state that we can consider terminal or that we want to stop at, and then we collect all the information that we have there and we back that up. And this is what we do, for example, in dynamic programming in value iteration. That's what we have seen that we were doing in practice. So in the end, all state space planning methods involve computing a value function because this is needed to improve a policy. And then we do this by doing this backup or backtracking of values. So in dynamic programming, we do something like that. But this is not the only approach that you can have. So now the difference between planning and learning, I want to stress that out again. I think I mentioned all of these things when we started discussing about reinforcement learning in comparison to dynamic programming, but let me repeat some of this. So in planning, you use simulated experience that is generated by model. In learning, you use real experience that is generated by the environment. This is the main difference. In model-based reinforcement learning, we will do planning, so we will simulate experience using a model, but this model will be learned by data that is generated on the environment, by the environment. So this is quite a big difference. Of course, this also implies that you can assess performance in a different way, also because in planning you can generate experience with a lot of flexibility. I mean, even if you're doing planning and your robot in simulation crashes on the wall, it's not a problem. If you're doing learning, reinforcement learning, and your robot crashes on the real world, that's a big problem. But if you have a model, sometimes you can replace some learning steps with planning steps. And this is what we do, for example, in QPlanning. So QPlanning is similar to QLearning, except that we will use a model. So it's a very simple algorithm where let's say you can select a state and a certain action randomly, then you send your state and action to your model, and then you obtain a next reward and the next state and the next termination, and you apply the tabular QLearning update. This is assuming that you have a model. If you have a model and you can say, okay, you start from this state, this is the action that I want to simulate, tell me what is the next state and action, sorry, the next state, the next reward, and the next termination, and I will apply my QLearning update rule. Except that this is QPlanning now because I'm using the simulated experience. Now, can I plug this inside some reinforcement learning method? The answer is yes, because you can do planning on an environment that is, on a model that is changing over time because you are improving it while planning. And that can be done, for example, by pure supervised learning, right? Because if you take a state and an action and you see a next state and a reward, the next state and a reward will become your labels for your supervised learning problem, where you can correct your prediction by these real data, real labels that you collected from the environment. So basically, in this setting, you're splitting your resources between model learning, decision making. So there's the planning part that can go in conjunction also with some reinforcement learning if you want, and the model learning part. So there are two processes that occur in parallel. So the experience, the real experience in the world will improve your model step by step. For example, in the form of a supervised learning problem, the experience will improve maybe your value function and the policy if you're doing also direct reinforcement learning on the environment. But at the same time, you can do also indirect reinforcement learning, which is this planning on this learned model. Oh, sorry, I'm changing all the slides by mistake. So this is the diagram of how things go in model-based reinforcement learning. So in reinforcement learning, model-free reinforcement learning, we only have this part, right? This is the standard reinforcement learning diagram where you have the word that generates experience that allows you to improve your value in the policy and the agent that acts in this word. Now, there is this additional process that is coming on the side where you're doing model learning. So you collect your samples, you improve your model, and you do planning on that, and use this to estimate your value in your policy. Okay, so let's look at one specific instance of this, which is the Dyna agent. So in the Dyna agent, basically you have exactly what we have discussed. You have a real experience that is used both for improving your model, so learning the model, and for doing direct reinforcement learning. The model is used at the same time for doing search and planning. Specifically, the Dyna agent can be implemented using QLearning and QPlanning. So this is called DynaQ. This means that for planning, we'll use QPlanning. For reinforcement learning, for direct reinforcement learning, we use QLearning. For model learning, we can use a table, for example, or a function approximator doing supervised learning. So we assume in this case, in this DynaQ agent, that the environment is deterministic, which is why we can use a table. So basically, we have a table, we have a record of transitions, and we assume that this, what we see happens in a deterministic way. So if we see a certain transition, we assume that to be true, and if this transition is overwritten, then you will overwrite your data, meaning that if you see, I mean, you assume the last transition on a certain state and action to be true, the last that you have seen. So then you can query your model on state and action pairs. And all of these in your mind should happen in parallel, even though this doesn't happen in parallel in practice. So for implementation, you specify the order. So this is the pseudocode. So you initialize your Q function as usual. You initialize your model as a table that can be queried by state and action. And then you loop, you start looping. So you take your current state, you take an action by an epsilon greedy policy. So you take this action, you execute this action, you observe the next state and the reward, and also the termination, actually. And then you do direct reinforcement learning using QLearning. So this is the usual thing. You put this information in your model. So you assume this is a deterministic table, which means you add an entry where you have SA that maps to R, S prime, and termination. And then you do, for a bunch of steps, some planning, where you take one random state from this table, one random action that was taken in this state from the table, and then you get the next reward and the next states and the termination, and use that for Q planning. Very simple, right? So it's really QLearning up to here, except that you have this additional model. You store your transition, and you use this table a bunch of times for taking a planning step. Now, if you compare QLearning to DynaQ, then you will see that with some few planning steps, your policy converges much early. So the steps per episode here are indicating how quick the agent is capable of reaching a terminal state. Mm. So this is telling us some information. If the agent is capable of reaching the terminal state in few steps, it means that it has learned to reach the goal quickly. Now you'll see that if you do pure direct reinforcement learning, it takes 30 episodes more or less to converge. With 5 planning steps, like in 3 episodes, it's almost there. 50 planning steps, it's almost there after 2 or 3 steps, which is quite interesting. This means that doing model-based reinforcement learning reduces the sample complexity of our problems. Sample complexity meaning that we require less data in order to be able to learn. Now, let me pause it here and we'll continue from here next time. I want to see if there are questions. So you don't. How can we be sure that the model is built in a correct way and then the planning is correct? You don't. But this is exactly the point. So you are assuming that that is correct and you are relying on that data. In the end, if that is a transition that occurred, it cannot be wrong. It's maybe something rare, but it's not wrong. It's a transition that happened in the real world. So it's not wrong. And then this means that maybe you're relying on rare data or maybe not perfect data, but still you're relying on some data that is realistic. Okay? Okay. Okay, so I think we can close it here if there are no more questions. And I'll stop the streaming in the meanwhile.